For millennia, humanity has looked to the sun, our star, as the ultimate source of life and energy. It is a celestial furnace, tirelessly bathing our world in warmth and light. Scientists have long dreamt of replicating this incredible power here on Earth. This is the essence of fusion energy. Unlike the energy we currently get from nuclear fission, which involves splitting heavy atoms, fusion does the opposite. It involves forcing light atoms like hydrogen to merge together under immense heat and pressure. When they combine, they release an extraordinary amount of energy, just as our sun has done for billions of years. This process is why we call these experimental reactors artificial suns. To build such a sun on Earth requires creating conditions that are almost beyond imagination. Inside a special donut-shaped machine called a tokamak, powerful magnets are used to contain a superheated gas known as plasma. This plasma must be heated to temperatures far hotter than the core of the sun itself, reaching hundreds of millions of degrees Fahrenheit. At these extreme temperatures, the atomic nuclei can overcome their natural repulsion and fuse together, releasing a burst of energy. It is a delicate and monumental undertaking, a quest to harness the very engine of the stars for the benefit of all life on our planet. The goal is to create a self-sustaining reaction, a tiny contained star that can provide a virtually endless supply of power. The fuel for this process, derived from hydrogen, is abundant in seawater, meaning we would never run out. The process itself is fundamentally safer than nuclear fission, as there is no risk of a runaway chain reaction or the creation of long-lasting, highly radioactive waste. For decades, this has remained a distant dream, but with each new experiment, humanity moves one step closer to making this dream a reality, fundamentally changing our relationship with energy and our planet. This journey is one of persistence and incredible ingenuity. Scientists and engineers from around the globe have dedicated their lives to solving one of the most complex challenges ever faced by humankind. They are not merely building a machine, they are learning to control the fundamental forces of the universe. The promise is enormous, a future where our cities are powered cleanly, where our air is free from pollution, and where the energy needs of a growing global population can be met sustainably. It is a vision of a world in harmony with its power source, a world powered by the same clean fire that illuminates the cosmos. In the pursuit of this stellar dream, a remarkable milestone was recently reached. In January of this year, scientists working with China's experimental advanced superconducting tokamak, or EAST, achieved something truly historic. They managed to create and sustain a plasma at a staggering temperature of over 180 million degrees Fahrenheit for an unprecedented 1,066 seconds. That is more than 17 minutes. For that length of time, a miniature sun, many times hotter than our own, burned brightly inside a laboratory, held in place by powerful magnetic fields. This accomplishment represents a monumental leap forward in our ability to control the untamed power of fusion. This achievement is not just about the incredible heat, it is about duration and stability. In the past, sustaining such extreme conditions for even a few seconds was considered a major success. The challenge has always been to keep the turbulent, superheated plasma from touching the walls of the reactor, which would cool it down and stop the reaction almost instantly. By holding it steady for over 17 minutes, the team at EAST demonstrated a new level of control. This shows that we are learning how to manage the complex physics of plasma, a crucial step towards building a reactor that can operate continuously day and night to power our world. The breakthrough was made possible by significant upgrades to the EAST facility. Scientists improved the systems used to heat the plasma, effectively doubling their power while ensuring the entire system remained stable. It is a bit like learning not only how to build a bigger, hotter fire, but also how to keep it burning steadily without it consuming too much fuel or collapsing in on itself. This delicate balance of power and control is at the very heart of the fusion challenge. The success of EAST provides invaluable data and proves that with careful engineering and deep understanding, long-duration fusion reactions are achievable. This record is a beacon of progress in a journey that has spanned generations. It builds upon previous records and pushes the boundaries of what we thought was possible. It shows the world that the path to fusion energy, while long and difficult, is one we are successfully navigating. Each of these milestones, from sustaining a reaction for a few seconds to now over 17 minutes, is a critical stepping stone. It provides the knowledge and confidence needed to design and build the next generation of fusion devices that will ultimately bring this clean energy source from the laboratory to our communities. The reason this tireless scientific pursuit matters so deeply is because of what fusion energy promises for our planet. Today, our world is largely powered by burning fossil fuels, a practice that releases harmful greenhouse gases into our atmosphere, driving climate change and polluting our air and water. Nuclear fission offers a powerful alternative, but it produces long-lived radioactive waste that requires careful and permanent storage. Fusion energy offers a way out of this dilemma. It presents the possibility of a power source that is both incredibly potent and fundamentally clean, a true revolution for our civilization and the natural world. The fuel for fusion, primarily isotopes of hydrogen called deuterium and tritium, is practically limitless. Deuterium can be extracted from ordinary seawater, an incredibly abundant resource. This means that fusion could provide energy for millions of years, freeing humanity from the geopolitical conflicts and resource scarcity associated with fossil fuels. A world powered by fusion would be one where energy is a universal resource, accessible to all nations without depleting the Earth's finite reserves. It is a vision of energy security and equity on a global scale, something our current systems cannot provide. Furthermore, the byproducts of the fusion reaction are benign. The primary result of fusing deuterium and tritium is helium, an inert and harmless gas, along with the release of energy. While the reactor components themselves will become radioactive over time, this radioactivity is short-lived compared to the waste from fission plants, decaying to safe levels within a century. There is no risk of a meltdown, as the reaction would simply stop if control were lost. This inherent safety and minimal environmental footprint make fusion an almost ideal energy source for a species hoping to thrive sustainably on its home planet. Imagine a future where vast power plants, humming with the contained energy of a star, provide electricity to our homes, industries and transportation systems without releasing a single puff of smoke. This is the future that the recent breakthrough at East helps bring into focus. It is a future where we can combat climate change not by reducing our quality of life, but by transforming the very foundation of our energy infrastructure. The quest for fusion is more than a scientific experiment. It is a critical part of our journey towards becoming responsible stewards of this fragile and beautiful planet. Despite the incredible progress, the path to a fusion-powered world is not yet complete. Several significant hurdles remain. The most fundamental challenge is achieving net energy gain, which means getting more energy out of the fusion reaction than is required to heat the plasma and run the reactor. While experiments like East have proven we can create and sustain the necessary conditions, we have not yet crossed this crucial threshold. Scientists must now refine their techniques to make the reactions more efficient, turning these experimental devices into true power generators that produce a surplus of energy. Another major challenge lies in materials science. The inside of a working fusion reactor will be an incredibly hostile environment, subject to intense heat and a constant bombardment of high-energy particles. We need to develop new materials that can withstand these extreme conditions for years on end without degrading. These materials must form the blanket that lines the reactor wall, not only surviving the harsh environment but also helping to capture the energy produced and breed more fuel. Finding or creating such durable, resilient materials is a monumental engineering task that is just as important as mastering the plasma itself. No single nation can solve these challenges alone. The quest for fusion is a testament to the power of international collaboration. China's work on East, for instance, provides vital knowledge for the enormous ITER, or International Thermonuclear Experimental Reactor project being built in France. ITER is a massive undertaking funded and built by a coalition of 35 countries, including China, the European Union, the United States, and Russia. It is one of the most ambitious science projects in human history, designed specifically to demonstrate net energy gain and test the technologies needed for a commercial power plant. The breakthroughs in one laboratory ripple outwards, accelerating progress for all. So, as we look to the future, we can be filled with a sense of informed hope. The challenges are real, but so is our capacity to overcome them when we work together. The recent success of China's artificial sun is not just a national achievement, it is a human achievement. It shines a light on a possible future where our energy is clean, our planet is healthier, and our potential is limitless. Imagine a world where the same incredible power that lights up the stars is quietly and safely powering our lives here on Earth. That is the world we are now one step closer to building.